Hello, class. We're back today with a few more examples of handling definite integrals with u-substitution. So let's start with this, the integral from 0 to 3 of e to the 2x plus 3. And here's something I recommend you do immediately when you look at a definite integral and think you're going to use u-substitution, which is to put an x equals in front of these numbers. And the reason for that is because these numbers are in terms of x, and the easiest mistake to make, which will of course cause you to get the wrong answer, is to forget to change these limits. That is, to forget to translate them to be in terms of u. Okay, so let's do that translation now. So I want u to again be my inside thing. So here the inside thing is this 2x plus 3. So du here is 2dx. And so now if I want to translate this, I'm going to write, well, this is an e to the u. Let's see. I need a 2dx. I only have a dx. So like before, I need to put a 2 here, but pay for it with a 1/2 out front. And so then I can translate, actually I'll leave the limits for now and I'll translate them in the next step. Okay, so now I can write this entirely in terms of u, so e to the u du, and now I translate the limits, and so x equals 0 becomes u equals what? Well, I plug x equals 0 into my defining equation that explains what u is. And so if x is 0, u is 3. And if x is 3, then likewise I plug 3 into this equation, and I get 2 times 3 plus 3. That becomes u is 9. And so this becomes the integral from u equals 3 to u equals 9 of this. And remember, we have this 1/2 hanging out front. And this 1/2 is hanging out front from our arranging for there to be a 2 in front of the dx. Okay, so this is now 1/2 times. And so now I take the antiderivative of e to the u, which remember is e to the u. Evaluated as u goes from 3 to u equals 9. Okay. Note, it's not that I didn't remember to take the antiderivative, it's that the function whose derivative is e to the u is e to the u. And so this is going to become 1/2 of e to the 9th minus 1/2 of e cubed, or if you want, it is e to the 9th minus e cubed over 3. Okay, that is our answer for this definite integral. Okay, now I want to point out something that might have gone by you that you might not have noticed in this pair of examples, which is that we actually saved work doing it this way over doing the indefinite integrals. Because when we did indefinite integrals with u-substitution, we always had to, as this annoying last step, we always had to put everything back in terms of u. So if you look at this example from earlier, you'll see that at the end, the last thing we had to do is say, okay, well, we had an e to the u plus c here, and so that was e to the secant of x plus c by translating back using this step. Okay, here we did not have to do that at all. We just did the integral in terms of u and got a number and squared that, or circled that, as our answer. Okay, so you might, if you're astute and curious, ask why? Why don't we have to translate it back? And the reason is because the answer to a definite integral is a number, and when we invented this new language, this language involving u's, that language didn't change what the numbers are. 2 is still 2. We just changed what x is to something involving u. And so since this is a number, there are no u's or x's in this answer. This is just a number, and numbers are the same in all languages for our purposes. So that's what happened here. And so remember, when you're doing u-substitution, you don't have to then change back at the end. Right? And so the two most common errors in doing u-substitution with definite integrals are to forget to change the limits, or to remember to change the limits, but then substitute back anyway. And so either of those will, of course, result in you getting the wrong answer. So you have to remember, make sure you do this step where you translate the limits. But once you've translated the limits and everything else, you never have to think about x again. You can do all the rest of the problem in terms of u. Okay, let's do another example. Let's do the integral from 0 to 3 of 10x over x squared plus 1 dx. I should re-emphasize, by the way, writing this dx on every integral you ever see is very important, because if you don't write it, it lets you not realize you haven't done that part of the u-substitution. But as long as you keep writing it every time and make that your reflex, then you won't miss that piece. Okay, so as I said, I'm going to start by writing x equals for each of these pieces. Then I have to write down what's my u going to be. So I think here my u is going to be this denominator. As I said before, if there's no u's in sight and you're looking at a fraction, try u being the denominator, because again, this x squared plus 1 is kind of living inside the world 1 over x. If I do that, then du is 2x dx. And so I really recommend, at the moment, pause the video and then try and translate this integral. You don't have to do the integral or anything. Just pause and just try and translate this integral from x language to u language. And I promise if you pause it, I'll wait here patiently for you, and then you can come back. Okay, now we're back. So I hope you tried this. But what's going to happen here is I'm going to try and find a 2x dx. And so what am I going to have to do to find a 2x dx? Well, I can factor this 10x. So I'll leave this as 5 over x squared plus 1 times 2x dx. And all I did here was say, well, 10x is the same as 5 times 2x, and I wanted a 2x, so I just rewrote it this way. And I've done this so that everything now will translate very smoothly. So this is the integral now of 5 over u du. And my x equals 0, that becomes, because of, again, this identity is the one I'm using, that becomes a u equals 1. And my x equals 3, that is going to become a u equals 10. And so now I do the integral. This is another common error, by the way, is to just get so excited that you just plug the 10 and the 1 into the 5 over u, but that's not the thing I'm supposed to do. I'm supposed to actually integrate this. That is, find the antiderivative. And the antiderivative here is 5 times the natural log of the absolute value of u. Okay, and it's evaluated from 1 to 10. And so this will be 5 times the natural log of 10 minus 5 times the natural log of 1. But please remember the natural log of 1 is 0, so this whole term drops out. And so the answer here is just 5 times the natural log of 10. Okay, I'll do a couple more examples in the next video, but you should have a pretty good idea now how to handle these kinds of definite integrals. But if you have any questions, definitely email me, post them in the forums, post them in the comments here. I'll see them no matter which of those ways you communicate it to me. But until next time, be well.